Okay, it's recording now. Hey, ladies and gentlemen, I'm back. So you may previously know me as the former peer tutor for MA3009. Anybody here familiar with me? Okay, it's okay. It's okay if you don't remember me. But now here I am returning as your MA3003 uh peer tutor. Yeah. So I'm quite excited to see how this semester will unfold. Okay. So without further ado, let's just begin. So this week is week 4, and so I'll be covering tutorial 3. Okay, I think tutorial 1 and 2 are sufficiently simple and manageable for students. Okay, so I'm just gonna start with this week's tutorial. So in this week's tutorial, and this tutorial I'm doing is the one that they gave last semester. I'm not sure if they modified it for this semester, okay, but I think it should be quite similar. Okay, so let me just get started with the first question. A 1 centimeter thick stainless steel of this grade is insulated with a 5 centimeter thick fiberglass on its outside surface. In a test with ambient air at 25 degrees Celsius, the steady state temperature of the insulation is measured to be 40 degrees Celsius. The outside convective heat transfer coefficient is estimated to be this. Okay, so here's some keywords. This means H, okay? It refers to H. As in, when you calculate the heat transfer, the rate of heat transfer, so Q dot, due to convection, it will be this HA T1 minus T2. Okay, we'll talk about what T1 and what T2 is. But for now, this heat transfer coefficient refers to this H. It's estimated to be this. So we are told that H is equal to 6, and the emissivity is given to be this. So this is epsilon. Okay, this is the Greek letter epsilon. Okay, draw a fully labeled thermal circuit representing the heat transfer processes. Sketch the temperature profiles through the stainless steel, insulation, and ambient temperature. State all assumptions. Okay. So let's go with the first question. They tell us to draw a fully labeled thermal circuit. Okay, so we have to understand what is a thermal circuit. And this circuit is a reference to electrical circuits, which is very, very similar to what we studied previously before. You remember MA2009? MA2009 was about electrical circuits. So a lot of us, right, we're all mechanical engineers, or some of us are aerospace engineers. A lot of us might wonder why we study MA2009, which is about electrical circuits. And this is exactly why we learn MA2009 for, is to link it back to MA3003. Yes. So the concepts we use here will be actively used in this topic and later on in the last topic. Yeah. So let me demonstrate why. Okay, so let me go to a fresh sheet of paper. Hold up. Okay, so let's try to draw the difference between electrical circuits and thermal circuits. So we have electrical circuits and thermal circuits. Okay, this is under MA2009, whereas this is under what we're learning now, MA3003. Okay, electrical circuits, we need to understand the various components of an electrical circuit. Okay, what we're using electrical circuits for is used as an analog. Okay, let me write that up. An analog. So electrical circuits will be used as an analog for thermal circuits. What does analog mean? Analog just comes from the word analogy. Okay, that means we will draw similarities between the concepts of electrical circuits and thermal circuits. So once you've already mastered electrical circuits, right, you will immediately understand the concepts of thermal circuits. It's just a matter of knowing which property is similar to which property. And I'll show you what I mean here. So think about it this. In electrical circuits, we know that what's flowing through the wires is current, right? Which we denote with I. So this is current. And what is current? Current is the flow of electrical charges, otherwise charge per unit time. Okay, charge per unit time, coulombs per second. In thermal circuits, what is a similar property to current? It is actually heat transfer, okay, the rate of heat transfer. So Q dot. Okay, by the way, right, this dot on the top, it means rate of, okay? So this dot means rate of, okay? Without the dot, it'll be just Q. Q is measured in joules. But then with the dot, Q dot is joules per second, otherwise known as watts. Okay, so this dot means rate of. It actually just means the same as d dt, okay, which is the rate of change, okay, rate of change of something. Okay, so in electrical circuits, what's flowing is current, but in thermal circuits, what's flowing is Q dot, which is the rate of heat transfer. Okay, now what else do we know in electrical circuits? In electrical circuits, we know the property of voltage, right? Denoted with small letter v, right? This is voltage. And what corresponds to voltage in thermal circuits? It's actually temperature, okay? The temperature T. Now, why is this the case? Okay, voltage and temperature are scalar fields, okay? They didn't mention this in the lecture notes, but it's important to know what this is. So a scalar field, if I give you a domain, okay, so a range of x, okay, this just shows your position, okay? No need to be frightened by this. This actually just shows your position. So a scalar field means at every position, there is some value of, let's talk about voltage first, okay? At every position, there is some value of V. Okay, for example, here there's one value, here there's one value, here there's one value, and so on. Okay. Same with temperature. Temperature is also a scalar field. At every value, at every position of X, there is some assigned temperature. So here it might be hot, here it might be cold, here it might be cooler, here it might be hotter, and so on. Okay. Now, the important thing to know of what makes them similar is this. Let's think about electrical circuits first. I give you a point, which we call a node, right? Do you remember? It's called a node. We call it node. Okay, let's say this is node A, and this is node B. Okay, in order for me to drive a current from node A to node B, what do I need? I need a difference in voltage values, right? Let's say this is positive 10 volts, and this is a positive 5 volts. See, they have a difference of 5 volts, right? Then I can drive a current from node A to node B. Okay, it always flows from higher potential to lower potential. Okay, higher potential to lower potential. But if both of them are 10 volts, right? Like if I change this to 10 volts, then there's no difference in the voltage values. So I cannot drive a current. Okay, then there will be no current flowing from node A to node B. And in fact, they're both the same node because they're the same voltage value. Okay, now let's talk about temperature. Okay, temperature, how temperature corresponds to voltage. Okay, let's just still call this node A and node B. Okay, so let's say this is temperature A and this is temperature B. Okay, in order for heat to flow from node A to node B, there must be a difference in temperature. You see that? You see how similar they are? For electrical circuits, I need a difference in voltage values between the two nodes. But in heat transfer, I need a difference in temperature in order for heat to be transferred, heat to flow from A to B. Okay, from A to B. So this will be my Q dot. Earlier it was I. Okay, I didn't label it, but earlier it was I. Now it's Q dot, where temperature A must be greater than temperature B. So let's say, for example, this is 100 degrees Celsius, and this is 40 degrees Celsius. Okay, see, temperature A is hotter than temperature B, so their heat transfer will be flowing from node A to node B. Intuitively, you would think something like, for example, a cup of hot coffee, right? If you have coffee, let's just say hot coffee. Oops, it's quite ugly drawing. Okay, Okay, you have a cup of hot coffee. The heat, let's say the coffee was just, it was just boiling water, right? So let's say it's 100 degrees Celsius, and then your outside temperature, your room temperature is 25 degrees Celsius. So you notice that your hot coffee will cool down over time, right? That's because here the coffee is hot while the room temperature is colder. So heat will flow from the coffee to the room temperature. Okay, then it cools down and then you are able to drink your hot coffee. Okay, so heat flows from high temperature to lower temperature. And what drives heat to flow is a temperature difference. Okay, that's how you draw the similarity between voltage and temperature. Okay, next we will look at resistance. Okay, in electrical circuits, we have electrical resistance, right? Which are things that impede current to flow. In thermal circuits, we have thermal resistance. Okay, there's no symbol to capture this, but I'll call it R term. Okay, we have thermal resistances. So electrical resistance is easy enough to picture, but what about thermal circuits? Thermal circuits actually corresponds to, okay, so let me just pull this aside. Thermal circuits actually correspond to the mode of each mode of heat transfer. Each mode of heat transfer. What do I mean by the mode of heat transfer? Remember, we have three types of heat transfer. There are conduction, convection, radiation. Each of this will represent a thermal resistance to your heat transfer. Okay, and I think that's about it. Yeah, that's about it. How we draw the similarities for electrical and thermal circuits. Now, you notice I pulled out three things, right? Voltage, current, resistance. And I purposely did this. Why? Because these three items is where you will use them in Ohm's law. Remember what's Ohm's law? Ohm's law states that delta V equals to I times R. And it's precisely this formula which we will use to calculate. Okay, so let me just say, okay, so actually you can rearrange this. You can rearrange this, right? So if I put I to one side, it'll be like this, and then delta V over R. Okay, it's just the same formula, but I rearranged it for I to become the subject. Now, in thermal circuits, we will also apply Ohm's law. Remember what I is? I, we say, is our rate of heat transfer, right? Which is Q dot. So Q dot will actually be equal to V is the same as, is similar to temperature, and then R is your thermal resistance. Okay, see? And let me just point this out as a side note. In MA3003, right, a lot of the questions, right, will always ask you to calculate one value. And 90% of the time, this value will be Q dot. Because that is the interest of heat transfer as a whole. In like the entire module, we are interested in finding the rate of heat transfer. So you're going to be asked to calculate Q dot a lot in this mod. Okay, so just want to point that out. Yeah, that's why I rearranged the formula to make Q dot the subject. Okay, because a lot of times we're asked to calculate what is the rate of heat transfer. Okay, see, so Ohm's law, we already learned that from MA2009. And then we're going to apply that similarly to MA3003 in heat transfer. And let me just point this out. While we are on this note, right, it is important to know the direction of the heat transfer because it will affect how you apply this formula. So let me explain what I mean. Recall when I was teaching MA2009, right? So if you're interested, you can view my YouTube channel to recap on MA2009. I actually think it's very important in this whole course of heat transfer. In fact, I dare say, right, that MA2009 is more important than thermodynamics in heat transfer. Okay, you can feel free to challenge me, but that's my opinion. Okay, so anyways, let's say for example, I have a voltage here. Okay, this okay, I'll call it V start, and then here will be Vn. Now, what do I mean by this? What does V start and Vn mean? So if I have this node which has a value of V start and this node which has a value of Vn, and the current flows from here to here, then to calculate I, it is given by delta V over R, right? Delta V over R. Okay, because we have an R, let me draw a resistor. So let me draw a resistor here with value of R. Okay, this delta V is given by V start minus Vn divided by the resistance it goes through. So V start is the node voltage value where the current starts from, and then Vn is the voltage value where the current ends its journey through the resistor. Okay, so let me just give you an example. If I want you to find the current of, let's say, okay, so this is 10 volts, this is 4 volts, and this is 3 ohms. Okay, if I want you to find this current, okay, so let's apply this formula. So V start minus Vn divided by the resistance, right? Oh, let me assign the current. So let's say the current flows from here to here. Okay, then this will be 10. Oh, sorry, I don't know what happened. Okay, 10 minus 4 divided by 3. So 10 minus 4 is 6. 6 divided by 3 is 2. Okay, so this is how you calculate current. Okay, let's say, for example, this is 8 volts, 2 ohms, 10 volts, and then but now your current flows this way. Okay, so where did the current start from? The current starts from here, right? So 10 volts is my V start. Okay, so let me just calculate the current. This current will be 10, and then where does the current end its journey through the resistor? Here, right? So the 8 volts will be by Vn divided by the resistance, which is 2. So 2 divided by 2, this will be 1 ampere. Okay, you must stick with this convention. Okay, the V start, the Vn, the direction actually matters, and same with temperature. Okay, so if I change this to, for example, 100 degrees Celsius, and then there's some thermal resistance, which is like 25 ohms. Actually, I don't know what's the units for the thermal resistance, but never mind that first. And then this is let's say 50 degrees Celsius. So the Q is given by the difference in temperature. So let's say the heat flows from here to here. So it starts from here, it ends at here. So 100 minus 50 divided by the thermal resistance, so 25. Okay, for example, something like that. So 100 minus 50 is 50. 50 divided by 25 is 2. And this is Q dot, right? So this unit will be watts. Okay, so you must stick with this convention. Okay, and we'll proceed to apply them in the question. Okay, sorry, this is a bit long-winded recap of 2009 and 3003, but it's essential to be able to draw the similarities between the two because you will widely apply them throughout the course. Okay, so now let's go ahead and draw this thermal circuit. Okay, actually, let me explain this R term, right? I didn't explain this fully yet. So there are 3 types of R thermal, okay, thermal resistances. One is conduction. So let's talk about conduction. And it also matters what kind of coordinate system you're using, okay? But let's stick with XYZ coordinate, okay? Because it's the basic coordinate system to start with. So in XYZ, let's talk about conduction resistance. Conductive resistance. Okay, I will label this as R conduct. Okay, each of the thermal resistances have their own formula. So for example, thermal conductivity is given by the formula L over Ka, where L is the thickness of the solid, K is the conductivity of the solid, and A is the cross section through which conduction is occurring. So let me draw out, for example, a wall. Okay, this wall is the shape of a cuboid, like a cereal box. Your heat is flowing in this direction. Okay, the cross-section area is given by this, right? It's the cross-section area through which it flows. The conductivity is the material, like for example, steel or fiber. And then L is given by this thickness. Okay, so I think that's simple enough. Now what about convective resistance? So convective, okay, resistance, whatever. So R convec. Okay, in XYZ coordinate system, it will be 1 over HA. Typically, H is given to you, is the heat transfer coefficient, which we talked about earlier. A is the surface area through which heat is being convected away. Okay, let me explain what that means. So let's say this wall, oh, this wall is losing heat through convection like this, right? It's losing heat through convection on this face. So this A will correspond to this surface area. Okay, but let's say what about a pipe? Okay, so this is a pipe, and then it's a hollowed out pipe. So let's say there's hot steam inside this pipe, and then heat flows out through this surface, right? It flows out through this curved surface area of the pipe. So let me just shade it. I'm referring to this area, and you must be able to calculate this area, which is given by the formula pi d L. Okay, d is the diameter of the pipe. L is the length of the pipe. So I'm referring to this length. Okay, I hope everyone knows that pi dl is a very basic formula since secondary school. Okay, so that it refers to, yeah, because your heat is being convected away from the curved surface area of this pipe. That's why this is this is the A that we are referring to. Okay. Now let's talk about the radiative resistance. So the radiative resistance is similar to the convective resistance formula, 1 over HRA. Okay, the R stands for radiation. Except HR is never directly given to you. Okay, HR is never directly given to you. In convection, H is directly given to you, but HR is not. Why? Because there's a special formula for HR. Okay, HR is given by the formula epsilon sigma T1 squared plus T2 squared T1 plus T2. Okay, T1 and T2 are the temperatures of the two bodies that are doing radiation with each other. Okay, epsilon is the emissivity. Sigma is called the Boltzmann constant. Don't worry about what the Boltzmann constant is. It's just a number, just like pi. Pi is just a number. Okay, and it's very easy to remember what the Boltzmann constant is. The Boltzmann constant is 5.67 times 10 to the power negative 8. Okay, you want to know how I remember it? 5, 6, 7, 8. Okay, and don't forget it's a negative 8. Okay, that's how I remember it. 5, 6, 7, 8, and don't forget the negative. Okay, there's a lot of formulas thrown here, but don't worry. Remember, MA3003 is open book, so feel free to concisely note down these formulas and apply them as you see fit. Okay, and yeah, so that's the three modes of thermal resistances, but this is only the XYZ coordinate. Now let's talk about the cylindrical coordinates. Okay, so in cylindrical coordinates, our conduction is given by, okay, this is a bit tough. Ln R2 over R1, 2 pi k L. Okay, so let me explain how you apply this formula. So suppose this is a cross section of a pipe. Okay, heat is flowing through this solid insulation. Okay, this ring that I draw here is an insulation. So R1 is the inner radius. R2 is the outer radius. Okay, K is the thermal conductivity of the insulation. L refers to the length of the pipe. So if I draw this pipe out, for example, like this is L, okay, the length of the pipe, which we talked about earlier, right? So that's how you apply this formula. Ln R2 over R1, 2 pi, right, over 2 pi KL. And then next we have for radiation and convective resistance, they're actually the same thing as XYZ. Yeah, they're actually the same thing. So R convec, it's just the same thing, 1 over HA. and R radiation is 1 over HRA. It's just the same thing. Okay. A is the surface area through which convection occurs, and this A is the surface area through which radiation occurs. Okay. I think that's about it. Okay, so now I'm going to start with this question. Yeah, I know there's a lot of theory to build up just to start with the first question. Okay, so if you find it hard to draw the thermal circuit right away, it's best that you draw the picture right away. So just draw what's going on. So for example, they give us this steel. So we're going to draw the steel wall. Okay, it's 1 centimeter. Okay, don't forget to convert everything to SI units. So cm, change it to meters. So 1 cm, and this is 5 cm. Okay, what did they say? They say this steady state temperature of the insulation is measured to be 40 degrees Celsius. The emissivity here is 0.8. Okay, the convective coefficient is H is equal to 6. Okay, and what did they say? They say the ambient air temperature. Okay, you must know this term. Ambient temperature, right? We symbolize it with the symbol T subscript infinity. Okay, ambient temperature, right, means the temperature of a surrounding fluid. Fluid doesn't mean only liquid, okay? Fluid means gas or liquid. Gas or liquid. So for example, a potato in a pot of water, and then the water is 35 degrees Celsius. Okay, this 35 degrees Celsius is the T infinity. Okay, or for example, a person in a room. Okay, the temperature of the room is 25 degrees Celsius. Okay, this surrounding fluid temperature, okay, the fluid I'm referring to is air, is the T infinity. Okay, so they tell me T infinity is 25 degrees Celsius. Okay, and this is steel. So this is AISI 302, and this is fiber. Okay, it's important to label this because it tells us the conductivity. And now we draw the thermal circuit. Okay, so this sketch will help us identify the thermal circuit. Okay, so remember what I said? Each mode of heat transfer refers to thermal resistance. So for example, this one, it conducts through this, right? So that means this will correspond to a thermal resistance, okay, a conductive resistance. Here also is also a conductive resistance, but it's a different value because the conductivity and the thickness is different. Okay, and then here we have radiation and convection occurring. Okay, there's radiation here and there's convection here. So how am I going to picture that? So let me move to this diagram down here. Okay, so this is the steel wall. This is the fiber resistance. And how am I going to show the convection and radiation? I'm going to show it like this. Two resistances in parallel. Why? Because they share the same node here. They share the same temperature node here. That's why I put them in parallel with each other. Because at this surface, both radiation and convection are occurring simultaneously, right? Both of them occur. Radiation and convection occur simultaneously. So they share the same temperature node. That's why I put them in parallel. Okay. And then here's the thing about this question. In the question, they never give us this T surrounding. Okay. Usually, right, for radiation, it will go off to T surrounding. But in this case, they did not give it to us. So we have to make one assumption. One of our assumptions is that T surrounding, okay, so we assume T surrounding is equal to T infinity, the ambient temperature. Okay, ambient temperature is not the same thing as surrounding temperature. Okay, it's not the same thing. Surrounding temperature refers to radiation. Ambient temperature only refers to the temperature of the fluid, temperature of the air only. Okay, if you're submerged in water, then it only refers to the temperature of the water. Okay, so ambient temperature refers to the fluid temperature, the surrounding fluid temperature. Temperature of the surrounding refers to everything giving me radiation. It's two different things. They might look similar, but it's not the same thing. But in this case, we had to assume they're equal because they never give us the surrounding temperature. Okay, so since they're the same, you will join them together like that. So this will be the T infinity, which is 25 degrees Celsius. Okay, and let's label this clearly. So this one is the surface of the wall, right? So I will label this at 40 degrees Celsius. This is the convective resistance, so 1 over HA. This is the radiative resistance, so 1 over HRA. This one, okay, first one is the steel. So let's call it L1, K1A. And this is L2, K2A. All the A's are the same, right? Because they all go through the same cross-sectional area. So all the A's are the same. But the thickness is different. That's why I label it L1 and L2. Then the conductivity are also different. That's why I label them as K1 and K2. Okay. They never really say what goes on here. Okay. So that's why I left it blank. So I'm just gonna assume it starts like that. Okay. So we have to write down our assumptions. So let me write down our assumptions. It might not be clear what these assumptions are, but bear with me. So assumptions. So we have steady state, 1D, constant K with each material. No heat generation. I'm just gonna call it heat gen, okay, just to be quick. And then constant and uniform H over surface. And T surrounding is equal to T infinity. Okay. So let me explain all these assumptions. Steady state means the temperature profile is fixed. It doesn't change with time. Okay. So what does that mean? For example, let's look at a point. Let me just draw a temperature profile. T versus X. So let's say a temperature profile looks like this. Let's focus on this point. This is 10 degrees Celsius. If it is transient, right? Transient and steady states are opposites. Okay. Steady state, transient. It's like cat and dog. Okay. It's like fire and water. They are opposites. So steady state means it is fixed like that. It's not changing with time. So if it changes with time, right? Okay. This is time equals to 1 second is 10 degrees Celsius. What about at time equals to 2? Then maybe it will become 20 degrees Celsius. Then time equals to 3. Then maybe you come 22 degrees Celsius. My point is that if it's transient, right, this temperature profile will actually change over time. But if it's steady state, it will just be fixed at what you see right now. It will be forever 10 degrees Celsius at that point, and so on and so on. Okay, it will just be stuck there. So, long story short, right, even if you don't understand that, what you're supposed to understand is when you see steady state, it means the temperature dt is equal to 0. Okay, it means your temperature doesn't change. If the temperature doesn't change, that means the rate of change of temperature is 0. And what is the rate of change of temperature? The temperature dt. Okay, so dt is equal to 0. 1D means heat only flows in one direction. Okay, and then temperature doesn't change in the other direction. Why is that okay? It's because that this is a wall. Okay, a wall means that a wall is thin in one direction. So this is the thin wall, but then infinitely large in the other direction. Actually, this right extends to infinity. This also extends to infinity. This extends to infinity. This extends to infinity. But then here is like, for example, a finite value. For example, just now they say 1 cm, right? Yeah. So a wall is very large in the other dimensions, but very small in a certain dimension, okay, which is the thickness of the wall. So that's why 1D is applicable. Constant K with each material, okay? So each material, right? The steel and the fiber, it doesn't change the value of K. There are some materials, advanced materials where, okay, at this position, K is for example, a value of 10 units, then K here will be a value of 5 units, then K here will be a value of 8 units. But don't worry, in heat transfer, there's never a varying K kind of situation. Okay, rarely. So constant K with each material, no heat generation. Okay, how do I know there's no heat generation? Because they never said so, okay? Heat generation, if there is heat generation, they will tell you, okay? So don't worry about that. If there's heat generation, they will tell you. Constant and uniform H, okay, it's because H, right, can actually change with the position on a surface. But don't worry about this now. This will be covered in the topic of convection. Okay, for now, in earlier topics, you just assume that it's constant and uniform. And then because they don't give us T surrounding, we just assume that's the same thing as the ambient temperature. Okay, so these are my assumptions. Why do we need these assumptions? These assumptions help us in simplifying the heat conduction equation later on. Okay, I'll tell you about that later on. Yeah, it might seem useless to you why you have the assumptions here, right? You just assume these things and then after that just go about your day. But it actually helps in the heat conduction equation. Okay, we'll come back. We'll cross that bridge when we get there. Okay, so we already done question 1A. Now let's do question 1B. Okay, I'm only going to do this question. The rest of it, I won't bother to do. Oh yeah, the sketching the temperature profile, I also won't do it. Okay, you can take my word for it. Trust me. So, how do we calculate the heat flux through the wall? Okay, the heat flux through the wall refers to the small letter q coming out from this wall. So you see, let's take a surface energy balance. Let me just erase this. Okay, when you look at this surface, what are the modes of heat transfer? We have convection and conduction. Okay, convection. So let me just write it down. So see here, the Q coming out of the wall is given by the convection plus the sorry. Did I say conduction just now? I meant radiation. Okay, convection and radiation. Okay, convection and radiation. So convection is given by H A T1 minus T infinity. Okay, T infinity is the surrounding temperature plus the radiation. So the radiation is given by epsilon sigma A T1 to the fourth power minus T surrounding, but then there's no surrounding. Okay, take note. The order of this matter, you cannot say T infinity minus T1 because this is the wrong direction. Why? Because this wall has a temperature of T1, okay, and it goes to T infinity. So where is it? T start and T end. This is the starting, this is the ending. That's why it's T1 minus T infinity, not the other way around. Okay. And same with radiation, okay? Same with radiation. Now, bear in mind, in this, right, you can keep temperature as kelvins or degrees Celsius. But then in the radiation, it must be kelvins. Okay, it must be kelvins. Okay, this is something to keep in mind. In the convection, you can keep it as Kelvin or degrees Celsius, but in the radiation, it must be kelvins only. Okay, so let's just plug in our values. So the values they give us, right, was okay. So H is 6. Oh, let me do something further. Because they ask for heat flux, right? Heat flux is not the same as heat transfer. Okay, this is heat transfer, but then this is heat flux. Actually, small letter q is actually big letter Q per unit area. So what are we supposed to do? We're supposed to divide both sides by area. So divide this by area, this by area, this by area. So this will cancel, this will cancel, and this q dot will be small letter q, right? This is actually just the formula of this. Okay, and now let's plug in the formula. Plug in the values as 6, 40 degrees Celsius minus 25 degrees Celsius plus 0.8 minus 5.67 and around -8. Then I already converted into kelvins, okay? So this 313 comes from 40 degrees Celsius, change to Kelvin. This 298 came from 25 degrees Celsius changed to Kelvin. Okay, if you calculate this, you should get 167.6 watts per meter squared. Okay, so that's how you do answer the second question. Okay, now we'll move on to the second question. Okay, how do we do this? So estimate the rate of heat flow. So the rate of heat flow, what they're saying, right, is find Q dot. So how do we find Q dot? This is a conduction problem. So they say they give us a truncated cone made of steel. The top diameter is 5 cm, perfectly insulated on all sides. So perfectly insulated on all sides means this side there's no heat flow, this side there's no heat flow. Okay, so that means heat can only flow like this. Okay, and not through the sides. Okay, so the base has a temperature of 184. The top has a temperature of 70 degrees Celsius. Assuming 1D, so it only flows in this direction. Estimate the rate of heat flow, mean find Q. Okay, so to find Q, because this is a conduction problem, we have to use Fourier's law. Fourier's law states that Q dot is given by negative K A dt dx. Normally, in easy problems, A is a constant, right? It's a fixed number. But in this case, is A a constant? No. Why? Because take a look at this. Okay, I'm going to invert the cone on its side. So it will look like this. Okay, now I'm going to assign a coordinate. The coordinate will look like this. So this is X, and this is my temperature. Okay, actually, let me put this be Y first, the Y coordinate. Okay, you see, as I travel along X, right, do you notice that the cross-section area actually turns smaller and smaller? See, this cross-section area is smaller, this cross-section area is smaller, this cross-section area is smaller. So that means A is not a constant. A is a function of X. So whenever I change X, my cross-section area will change. So, right, I cannot just write this as A. I need to write A of X. Okay, I hope you understand that. So how do we go from here? Okay, so we need to rearrange this first. How do you rearrange it? So, okay, let me move A to the left-hand side. So it become like this. Okay, and then everything else remains. Then what I'm going to do is put this dx to the other side. Now, why do I do that? So that I can perform integration now. Okay, so I'm going to integrate both sides. Okay, so I'm going to integrate this from 0 to, okay, let's take a look. See, they said that the height of this cone is 5 cm, right? So this is actually 0 to 0.05. Okay, 0.05 is in meters. So I'm going to integrate this from 0 to 0.05. Now, what about the bounds of the temperature? You need to fill the bounds of the temperature, right? That is given by the base in the top temperature. So this and this. So from 184 degrees Celsius to 70 degrees Celsius. Okay. Now, here's our problem. We can integrate this, right? I think this is easy to integrate. But what about this? 1 over ax. We don't know what's the function of ax, so we had to find it out ourselves. And here's how you find it. So let me just copy this diagram again. Now, we ourselves have to make this function a of x. And this is how I'm going to show you. So using this graph, we're going to have to formulate our own equation that describes this line. You'll see why. Okay, so okay, for a straight line, right, we need 2 points. And we just happen to have those 2 points, this point and this point. What's the coordinate of this point here? This is 0. Now, what did I say? The bottom diameter is 10 cm. So that means the bottom radius is 5 cm. Okay, so this height is actually 5 cm, which is 0.05. Okay, I hope you all understand that, right? The bottom is 10 cm, the radius is only 5 cm. That's why it's 0.05. And then what's this coordinate? This coordinate will be 0.05. And the top radius will be 2.5 cm. Okay, the top radius is 2.5 cm, which is actually 0.025. Okay, with these 2 points, we can formulate the equation of this straight line. Okay, and do you know what actually this value is? All these y values, right, are actually the radius. So instead of calling this y, I can call this r. Okay, you'll see why I will label this r. So remember, if you want to find the straight line equation, we had to go back to secondary school, and the formula is y minus y1 over x minus x1 is equal to y2 minus y1 over x2 minus x1. Okay, y will just be a variable, so you keep it as r. Then y1 is a known y value. So let me see my working. Yeah, I've chosen this 0.05. So I chose this coordinate. Okay, divided by x minus 0 is equal to, now I'll take this coordinate minus this coordinate. Okay, so 0.05 minus 0.025, 0 minus 0.05. Okay, now you slowly make r the subject. Eventually, you will get this. Okay, now how am I going to use this to find my a of x? Remember, our mission here is to find a of x. What is the shape of the cross sections here? Remember that the shape of the cross sections are all circles. Okay, what is the formula for area of circle? Area of circle is given by pi r squared. But you see, the radius here changes with position. So it's not, and also the cross-section area. So this cross-section area is not just a, but it's a of x. And same with the radius. The radius is not a fixed value. It's not just r, it's r of x. Okay, and what is this r of x? This r of x is actually just this. Okay, so that's why I'll just substitute it in. I'll substitute it in. Look at this. Okay, yeah. So this is my a of x, which we will sub it into our equation. So this a of x, we will sub it into here. Okay, so this is no longer a of x now. I'll put this as the pi negative 0.5 x plus 0.05 squared. Yeah. Okay, now let me tell you something. To find this k, right, you need to use the average value, the average temperature of the stainless steel cone. So the base was 184, right? And then the top was 70 degrees Celsius. So divided by 2, you get 127 degrees Celsius. In kelvins, this is 400 Kelvin. So when you go to the textbook, right, and then you find the conductivity of stainless steel, you go find the value of the K at 400 degrees Celsius. Okay, find the value of K at 400 degrees Celsius. If you do that, you should get a value of K of 15.2. Okay, 15.2. Okay, so we will sub K as 15.2. Okay, so let's just continue. Okay, I'm not going to integrate this for you. You can just put this in your calculator. Okay, integrate this in your calculator, and you should get 12.73 here. And then here, you substitute in all your values. So your values will be what? Negative 15.2, the conductivity. And then this, right? Sorry. So integration of temperature like this will just be T. And then you sub in your limits, right? Which is 184 and 70. So that's why this will be just 70 minus 184. Okay, and then you make Q the subject, eventually you will get 136. Okay, 136. Let me check if this is the answer. Yep, yeah, that's the answer. 136 watts. Okay. Okay, now I'm gonna move on to the next question. Okay. A backlight coating is used with a 10 mm diameter conducting rod whose surface is maintained at 200 degrees Celsius by passage of electrical current. The rod is in a fluid of 25 degrees Celsius. Okay. So fluid means this temperature is T infinity. Okay, you have to remember what symbols refers to what. And okay, convective coefficient. So this refers to H. What is the critical radius? Now, let's understand what's the concept of critical radius. But let's understand what's the picture first. So let's say this is a rod with some heat that's going to flow outwards. Okay, it's going to flow outwards. Then I wrap it in some insulation. Okay, so it's going to conduct through the insulation and it's going to convect to the surrounding fluid. Okay, basically the air around it. So the critical radius is the thickness, or sorry, the radius of the insulation. So this radius, the radius of this insulation at which the heat transfer will be maximum. Okay, the radius at which the radius of the insulation at which heat transfer will be maximum. Okay, so if I wrap the pipe with this thickness of insulation, then the heat loss will be maximum. Okay, so the lecturer already got the formula out for us, and then we can just use it wholesale. It's just K over H, right? So let me just get the business first and then substitute it in. So let me check. Yeah. Okay. The backlight conductivity, you can find it in your book, okay? In your book. So the data will say K is actually H. This is found in the textbook. And then the value of H is given to us 140. So this will be 0.01. That's how we get the answer. Okay. Now, let's explore how do we get this formula. It seems very simple and elegant, and it's actually very easy to derive. Okay. So let me just derive it for you. Now, we have to calculate the total resistance of this heat transfer. So there's one resistance here, conductive resistance, and then there's another resistance here, convective resistance. So remember, this is a cylindrical problem, right? So let me just call this R total. There is the conduction, there is the convection. Okay, remember, conduction is given by ln. Okay, let's call this radius R. Okay, let's call the inner radius R1. Okay, it's given by ln R over R1 divided by 2 pi KL. And then the convection is given by 1 over HA, right? A is the surface area through which conduction is occurring. Then where does it occur through? It occurs through here, right? It's being convected away from the surface. And then how do I calculate that surface area? This surface area will be given by 2 pi r, the circumference, times the length. Okay? Now, we want to find the radius, we want to find the value of r at which Q is maximum. Okay, in other words, this is the same thing as asking the R at which R total is minimum. Why? Let us think about it. Q maximum, right? It's like saying your current is the maximum. Your current will be maximum when your resistance is the minimum, right? That's why I say if you want to maximize your heat transfer, you must minimize your thermal resistance. Okay, so that's why these two are actually the same thing. Okay, they're equivalent. Okay, so remember in just basic high school differentiation. So let's say if I want this graph, right? And then I want to find this point where it's minimum. So what will you do? This is given by y. What you will do is dy dx equal to 0, and then solve for the value of x. This is exactly what we're going to do here. So in this case, what we do is dr total dr equals to 0 and solve for the value of r. Okay, so this is my r total. I'm going to differentiate it first. Okay, so I differentiate this. So these are all constants. I will just take them out. Now we're differentiating ln, right? To differentiate ln, it'll be 1 over the inside times differentiation of the inside, because chain rule. So differentiation of this inside will be just 1 over r1 plus, now differentiating this. Now, the rest of these numbers are actually just constants, right? So what do I mean? H, 2, pi, L. H, 2, pi, L, all of these are constants. The only variable is r. So that's why I will separate it out. So that means I'm trying to differentiate 1 over r. Okay, which is the same as differentiating r to the negative 1, which is the same as power bring down, power minus 1. So this will become negative 1 over r squared. Okay, now let's see if we can simplify anything. Yes, we can. This r1 can cancel this r1. Then let's see what else we can cancel. Both of them have 2 pi. Both of them have 2 pi. Both of them have L. Okay, what do I mean by both? I'm referring to this term and this term. Okay, both of them have L. And that's it. That's it. So I'm gonna multiply them together. So this will become 1 over r. This will become negative 1 over r squared. Okay, now to simplify this, I will multiply both sides by r squared. Okay, so the first term will become r over k. The second term, see, this r squared will cancel with this r squared. So it become 1 over h equals to 0. Then you move 1 over h to the other side, and then you make r the subject. Ta-da! This is your r critical. Okay, so this is the radius at which the insulation will maximize your heat transfer. Okay? It will maximize your heat transfer. So this is how you derive that formula. Okay, now what is the heat transfer per, now I'm going to go to question B. What is the heat transfer per unit length? Okay, so what does this mean? This actually means Q per L. Okay, heat transfer per unit length of the rod with a coating of a bakelite which corresponds to the critical radius. Okay, so let's see what that means. Okay, so let's draw the picture out. So this is the rod. This is the bakelite. This radius is 0.01. Okay, and this, right, because they say the diameter is what? They say the diameter is, let me see again. The diameter is 10 mm, which is 1 cm, which is actually 0.01, right? So 0.01 divided by 2 will give me a radius of 0.005. Okay, I hope this is clear to everyone. Where did I get this 0.01? This is the R critical that they say just now, right? They say now the bakelite corresponds to the critical radius. Okay, and then remember the temperature that they give us here, right? They say it's 200 degrees Celsius. Yeah, that's what the question said. Yeah, here. Okay, so now they want us to find Q per L. Find Q per L. And how do we do that? We just use Ohm's law. Okay, remember Ohm's law is given by this, which is delta T, over the total resistance. Okay, the temperature, now let's look at the heat flow. The heat flows from here and then goes to the ambient temperature. So it starts at 200 degrees Celsius and then it ends at T infinity, which is 25 degrees Celsius. Okay, so it starts from here, ends at here. So meaning to say, this will be 200 minus 25 divided by the total resistance. The total resistance is given by what? It's given by this conduction and this convection. Okay. So the conduction is given by the formula ln R2 over R1, right? So R2 in this case will be 0.01. Then R1 will be given by this divided by 2 pi K times L plus 1 over the 1 over HA. So 40 times 2 pi R times L. Okay, so how are we supposed to squeeze out the value of Q over L? Now this is how we're going to do it. We're going to divide both sides by L. So divide this side by L and divide this side by L. Okay. So let's observe what happens out here on this side. You'll see that all the L's will cancel. Why? Okay, the numerator multiplies by the numerator. So this times 1 is just the same. So we can ignore the numerator, the effect on the numerator. But what about the denominator? See, in the denominator, we have these terms multiplied by L, right? So you see, this L and this L will cancel. Then likewise, actually, this L will cancel out with this L also. Okay, so that's why in the end, right, all the L's at the bottom, actually all the L's on this side will disappear. And all of these are just numbers. You see, it's just 200 minus 25 divided by ln 0.01 divided by 0.005 divided by 2 pi 1.4 plus 1 over 140. Yeah, all these are just numbers. You punch them all in your calculator, and then in the end, you should get 769.7 watts per meter because it's per unit length. Okay, I hope this is clear. Next, we go to C. So how thick should the backlight be? How thick should the backlight coating be to reduce the heat transfer associated by 25%? Okay. So what does this mean? They're saying, right, we need to find the thickness so that the new heat transfer per unit length is 25% less than the original. 25% less, right, means 75% of the original. Why? Because the original is 100%. 25% less means 20, this minus 25. So now we're trying to find Q dot per L new. The new one is 75% of the original. Okay, this is the original that we found. The original that we found just now was 769.7, right? And then you calculate this should be 577.268. Okay. Now, how do we find Q per L new, the new one? Again, you just use the Ohm's law from earlier. In fact, we can just copy from the working that we got earlier. So this, right, nothing has changed. Nothing has changed from here. So let me just copy this. This thing, hold on. Let me copy this. Copy, paste it. Nothing has changed here except for R2, right? Because now they're asking for the new thickness. So that means R2, the outer radius will change. So this R is different now. Then anything else Yes, this is no longer 0.01. This is R. Okay? Everything else remains the same. The temperature difference is the same. The inner radius is the same. There's still conductive resistance. There's still convective resistance. The only thing that's changed, right, is the thickness of this insulation. So that's why I replace it with R. Okay? In fact, this L is already gone. So let me just erase this away. So this is gone. This is gone. This is gone. Okay? Then, remember what we said just now? This value is equal to this. So that means I'm going to replace this side with 577. Okay? This will be 577.268. And then this thing, I just copy it down. Okay? Now, how are we going to solve this for R, right? It doesn't seem easy. Now here we're going to use our graphic calculator. So using graphic calculator, I'm going to show you how to do this. So bear with me. Okay, give me a moment. It takes some time to load. Okay, you should see my calculator right now. Okay, what I'm going to do is I'm going to add graphs. Okay, so now I'm going to plot out the graph. So how do we do it? We're going to plot each side of the graph. So yeah. So remember, on one side we have 577.268. So this is one value of the graph. And then another graph is the other side of the graph. So let me just plot this down. It'll be the 200 minus 25, the giant fraction, basically. Okay. So ln, okay, ln, yeah. Okay, so now the variable is the R, right? So I will label it as X divided by 0.005. And then this will be 2 pi times 1.4 plus the convective resistance, so 1 over H times the surface area, which is 2 pi X, right? Again, this is a variable. So let me check that. 200 minus 25, conductive resistance plus convective resistance. Okay, now we're gonna have to zoom out. So the zoom bit. Okay. Now we have to find the intersection between these two. So the intersection, I can use my calculator like this. Yeah. Okay. So one intersection is here. Actually, there's another intersection somewhere. Hold on. Let me zoom in again. Zoom in. Yeah, it's not very obvious, right? But you have to zoom in. There's actually two intersections. Another intersection will be, oh, let me find the intersection. The intersection will be here. So one intersection will be 0.03. Another intersection will be 0.061. There are two answers, right? We have to see which one is the sensible answer. Okay. So let me go back to my OneNote. Okay. So our graphic calculator told us there are two answers. One possible answer is 0.03. Another one is 0.061. Now, let's see what happens if it is 0.03. Take a look at the diagram that we labeled. This diagram I'm referring to. You see, 0.003, right, Can it be this outer radius? It cannot. Why? Because the inner radius is 0.005. 0.003, 0.005. How can 0.003 be the outer radius, right? This is contradicting because 0.03 means it'll be the inner radius now. Okay, 0.003 is less than 0.005. That means it cannot be 0.003. So we reject this answer. Reject. Because, okay, this means because 0.003 is less than R1. Okay, this is the reason why. So our answer is this. But this is only the radius, right? They ask for the thickness. Okay, so how do you calculate thickness? The thickness is given by this, right? Which is the R2 minus R1. That's how you find the thickness. Okay, so thickness is given by R2 minus R1, which is here. That's how you get an answer. Okay, so this is how you find the thickness. Let me check. Yeah, that's correct. Okay. Okay, now we have to move on to the last question. Yeah, I'm not covering all the questions, but because as you can see, right, we're already using 1.5 hours. There's no way I can cover so many questions. Okay, I'm sorry. If you're interested in the other questions, please seek your professor's help. But I'm covering the most important ones in the important selections. Okay. Okay, this is an important question. This kind of question is called heat conduction problems. They're basically differential equation problems. Okay, heat conduction problems. Now let's read the problem. The outer surface of a hollow sphere. Okay, you know what? Let's forget about this question first. Let us see how do we approach a heat conduction problem. How to solve a heat conduction equation. Okay, that is called heat conduction equation. Heat conduction equation problems. So this is the recipe. Number one, select the correct equation. Number two, simplify with assumptions and info. Okay, the given info from the question. Number three, solve C1 and C2, which are unknown constants using the boundary conditions. And then number four, find T of X, the temperature distribution. Okay, T of X is called the temperature distribution. Okay, it's always this set of steps. Select the correct equation. Simplify with the assumptions and the information. The information is given in the question. Solve the unknown constants C1 and C2 using the, boundary conditions. Okay, BC is boundary conditions. Solve the unknown constants using the boundary condition, and then you find your temperature distribution. This is how you do it. Okay, so how do you select the correct equation? Selecting the correct equation is very obvious. It depends on the shape of the object. Okay, if it is a cylinder, if it is a pipe, if it is a rod, then you use the cylindrical equation. Okay, you use the cylindrical equation. If it is a ball, if it is a sphere, then obviously use the spherical equation. Okay, let us take a look at the equations. You see? Cartesian means x, y, z. Okay, cylindrical, the variables are r, theta, z. Spherical means the variables are r, theta, and phi. Okay, so if the object is a cylinder, then you use the cylindrical. If the object is a sphere, then obviously use the spherical. Anything else, and mostly this is a rectangle, not necessarily a rectangle. There are some cases where I see it's not a rectangle. Then you use the Cartesian. Okay, so step one is very easy. Step two, simplify with the assumptions and the information. Okay, I think it's best if I just go through the question to see what step two looks like. Okay, solve C1 and C2. Okay, from here on, let's just dive right into the question. Okay, it's better to just show you what I mean. Okay, so the outer surface of a hollow sphere is given by R2 and is subjected to uniform heat flux given by this magnitude. It is a magnitude. The inner surface is R1 and is held constant at a temperature of Ts1. Develop an expression for the temperature distribution T of R in the sphere in terms of these unknowns and the thermal conductivity of the material is K. Okay, so step one, choose the correct equation. So can you tell me in the chat, which shape should I use? They say a hollow sphere. So which equation should I use? Tell me in the chat. Faster, faster. Should I use Cartesian? Should I use cylindrical? Or should I use spherical? Anyone tell me? Hello, Ben? Yes. Okay. Correct. Spherical. Because obviously there's a hollow sphere. So obviously just choose spherical. Okay. So we're gonna use this equation, right? So what you would do is because this is an open book exam, you will bring your lecture notes, right? And this page is very important. So find this page of the slide and mark this important page because nobody can remember all this, right? So you're just gonna use your cheat sheet and remember this. So we're gonna use spherical, right? So let me just clean this up. Let me use my snipping tool. Okay, so now you copy and you paste it from your lecture notes. We're gonna use the spherical equation. Okay, that's step one. Step two says simplify with the assumptions and the information. Okay, so what information did they give us? Okay, you see, what is the variable in this question? We have T of R, right? Do you notice that there's no time inside here? There's no time inside here. So this is a clue that this problem is a steady state problem. Okay, it's a steady state problem. That means the temperature doesn't change with time. So we assume that this is a steady state. So one of our assumptions is assume steady state. Okay, and remember, just now I said steady state means partial temperature, partial T is equal to 0. Okay, so how are we going to simplify? You see this? Throw it away. It becomes 0. Okay, so we assume there's steady state. What else? Okay, we're going to assume that this is a 1D problem. Okay, and in fact, it is a 1D problem. Why? Because look at the variable inside here. The variable, right, is only R. They didn't say the temperature varies with R, theta, phi, or T. See, these other variables, they don't show up. See, theta doesn't show up, phi doesn't show up, time doesn't show up. So that means, right, temperature is independent of theta and phi. Okay, independent of theta and phi. What do I mean by independent of? Okay, let's take, for example, this statement. T is independent of theta. So this means partial temperature, partial theta is 0. Okay, likewise, if I change this to phi, then this means partial temperature, partial phi is equal to 0. Likewise, if I say independent of Z, then that means this one, partial temperature, partial Z is 0. So how does this help us simplify? Take a look. Right? So we assume that it doesn't depend on phi, it doesn't depend on theta. So you see this? This will become 0. You see this? This will become 0. And then, did they say there's any heat generated? No. So we just assume there's no heat generated. So this also becomes 0. So, yeah. So this is part of our simplification. Yeah. In fact, I think this is simplified enough, right? Simplified within the assumptions and information. Yes. Okay. This is sufficiently simplified already. Sufficiently simplified. Okay. So now let's just write down what's left. So what's left is the first term. Equals to 0. Okay. Another thing we're going to assume, right, is K is constant. Right? K is constant. So assume K is constant. Okay. This assumption is important because when you know K is constant, right, you can take it outside of the derivative. Okay, you can take it outside of the derivative. Why? Let's do, for example, d dx of 5x. You know you can take this 5 out, right? Because it's a constant. So this is the same as 5 times d dx x. Okay, you can only take out this 5 because it's a constant. Okay, likewise, you can only take out this k outside because it's a constant. Okay. Okay, sorry, my laptop is a bit laggy. Okay, but for example, right, d dx of x ln x, you cannot take out this x outside because it is a variable. Okay, x is a variable, so you cannot take it out. That's why the assumption that k is a constant is important, because it allows us to take it outside of the variable. I mean, take it outside of the derivative. So this 1 over r squared, I'm going to bring it to this side, so it will disappear. Okay, it will disappear because I multiply both sides by r squared. So r squared here, r squared here. So this cancels with this. Then I'm left with this. Okay, our job is to solve for the temperature distribution. So basically, we want to make this our subject. So we have to move it, we have to keep it on one side. So we need to remove this derivative. So let's integrate, right? Because integration is the opposite of differentiation. Integrate with respect to r. Okay, so if we integrate this, this will cancel with this. And then we're left with the things inside. Uh, Let me check my solution. Yeah, okay. Okay, sorry. I'm wrong, huh? Integration of 0, right? Integration of 0 is just 0. But then after you integrate, you must add their arbitrary constant. So this will be C1. Okay? Then we'll move kr squared to the other side. So it becomes C1 divided by kr squared. And then we're left with this. And now we again integrate dt dr. Integrate. Integrate. So integrate with respect to r. So this will cancel with the differentiation. And then what we're left here on this side is temperature. This side, okay. So C1 and K are constants. So what we're doing is we're integrating 1 over r squared, right? Which is same as integrating r to the power of -2. So power plus 1 divided by new power means that this will become negative 1 over r squared, right? So this will become negative 1 over, oh, sorry, negative 1 r to the 1. Wait, oh my god, my laptop is lagging to hell. Okay, sorry. Okay, and don't forget at your arbitrary constant. Okay, so that's it. This is actually T of R, but we don't know the unknown constants C1 and C2. So we need to solve them using the boundary conditions. Okay, the boundary conditions. So let's have a look. Okay, how do we get the boundary conditions? It's given by the question. Let's read the question again. See, at R1, it is held at a constant temperature of Ts1. So what does this mean? This means at R1, T R1 is equal to Ts1, right? The inner surface is being held at a temperature of Ts1. So that means T at R equals to R1 is equal to Ts1. So what are we going to do? We're going to substitute R1 into this equation, right? So C1 over K times negative 1 over R1 now, not just R, plus C2 is equal to Ts1. So this is our first equation. Okay. Now let's look at the second boundary equation. Yeah, I'm just making sure my answer is correct. So the second boundary equation is at R is equal to R2. Now, what did the question say? Now let's read the question. The question say at R2, it is being subjected to a heat flux. So that means we're blowing heat at the outer surface. Okay, we're blowing heat of Q2 at the outer surface. Okay, so at R equals to R2, let's take a look at the physical phenomena of this problem. So at the outer radius, right? So let's draw a control volume because we're going to take a surface energy balance. There is a heat flux. So they never told us the direction of the heat flux. So let's assume it moves this way. Okay, you can also make it point outward, but I'm going to point it inward. It's just an assumption. This is Q2. Okay, and then because this is a solid sphere, right? There's also conduction. Yeah, there's also conduction. Sorry, I assume my conduction is pointing inwards. Okay, so this is my Q conduction. Okay, now at this outer radius, right? Here is the problem. So let's see the energy balance of this. See, the heat going in is Q2, and the heat going out is the Q conduction. So Q2 is equal to Q conduct. Okay, and then using Fourier's law, we can change Q conduct into negative K d T d R. But then this occurs at R is equal to R2. So we need to put this R is equal to R2. You must, okay? Because it occurs at R2, so you must put that. Okay, and then notice this also. You see, my Q conduction, right, is going radially inwards. This is against the positive radius direction. What do I mean? Because normally, right, the positive radius direction is actually, okay, this is the radius center, pointing outwards. This is positive R. But then if it points radially inwards, right, okay, if it points towards the radius, this will be negative R, in the negative R direction. So since my Q conduction is going towards the center, this is following the negative R direction. That's why I must assign this as negative. Okay, it's very important to get clear the direction. Okay, because it's pointing radially inwards. This is following the negative R direction, so I must assign the Q conduct as negative R. Yeah, negative Q. Okay, negative Q. Okay, so this minus can cancel with this minus, and then okay. So how do we go about simplifying this? So what we're left here is K dt dr, where R is equal to R2. Now, how do we find this? Let's go back up. dtdr. Let's try to find where's dtdr. Actually, right, dtdr is given by this. dtdr is equal to c1 over k times r squared. So we're just going to copy, we're going to replace dtdr with c1 over k times r squared. We go back down. But instead of r, this would be r2 because we said r, oh, sorry. We said r is equal to r2. Okay, that's why. So notice that this k can cancel with this. And then if you make c1 the subject, you will get, oh sorry, q2 r2 squared. Okay, now we need to, don't forget, we need to find c2, right? So how do we find c2? Remember this, the equation 1? Yeah. This equation, we're going to sub our c1 into here. We're going to sub our c1 into here. So okay, so we get this. Okay, and then you make c2 the subject, you'll get okay. Yeah. Okay, so let's review our steps. So the first step, we selected the correct equation. It's a spherical equation. Then the second step, simplify the assumption with assumptions and information. Okay, we already simplified that. Then we already solved for C1 and C2. Now we have to find the temperature distribution, which is what they want, right? So after you found C1, after you found C2, we're going to substitute it back into our equation for T of R. Remember this equation? At first, we don't know what C1 is, we don't know what C2 is, but we already found it. We already found C1, we already found C2, so we're going to substitute this in and then finally get our answer. Okay, so sub C1 and C2 into T of R. Okay, so what we get is okay. Actually, you can just stop here, but for the purposes of beautification, I'm gonna factorize it, okay? So this term and this term, I'm gonna factorize out the common terms. So factorize this. Then the only terms that remain, right, will be this 1 over R1, then minus 1 over R, then plus this. Yes. Okay, that's how you get it. Okay, so let's go to the second question, which is also the last question. So the last question, okay, they give us some values. What do they want? Okay, they're saying find Q2. So they give us the radius, they give us outer surface temperature, inner surface temperature, and then they give us the K. So find Q2. So how do we do this? We're going to use the information they give us. So they told us that the outer surface temperature, right? So the outer surface is at a radius of R2. The outer surface is at a temperature of TS2. Okay. Then this is this. Okay, so let's just copy it down. Oops. Except now R is R2, yeah. Okay. And then now we're going to substitute in all the known values and then find Q2. So Q2 is unknown. We're going to find it. R2, they give it to us. K, they give it to us. R1, they already give us. R2, they already give us. TS1, given. TS2, given. Now we just make Q2 the subject and voila. Okay, but you notice my answer is positive 3000. But how come the lecturer, his answer is served as negative 3000? And it's because of the direction I assume. Okay, the direction I assume is inwards. But the lecturer probably assumed that the direction flows outwards. So what the lecturer did is he assumed an incorrect direction. He assumed an incorrect direction. So his answer will be evaluated as negative 3000. So the negative will tell him that the assumption is wrong. So what he has to do is flip the direction of his assumed Q2. Okay. But since my one is positive, it shows that my direction is correct. Okay. And that's it. That solves the question. Okay. So this is the end of the first PTP session of 3003. Okay. I'm going to upload this on YouTube and then that's all. See you next time. Okay. Bye-bye. Everyone's dismissed. Okay. Thank you, Brian. Yeah, you're free to leave already. Okay.